You are about to listen to the 365 Days of Astronomy podcast.
What do they talk about?
Astronomy, stuff that's far away.
How far?
How far? Well,
this stuff is far. It's really far. This stuff is far, far, far away. We're talking far. Like uber far. You can't get there by car a day. It's super duper crazy far, but not just pulsars, quasars, and stars. We mean it's far. Far, far, far. If there's some doubt, listen to a shout. This stuff is far.
the IYA 365 Days of Astronomy podcast starts now.
Hi, I'm Emily Lakdawala, blogger for the Planetary Society at planetary.org/blog. Today, September 4, 2009, is the day that Earth passes through the plane of Saturn's rings. Ring plane crossings like these are priceless events for planetary astronomers. In today's podcast, I'll touch on the discoveries we've made during past ring plane crossings and explain why this one will sadly turn out to be a bit of a dud. The solar system is a playground for lovers of geometry. Slicing up the solar system are numerous planes containing the orbits of every body that circles the Sun. All of these planes intersect at the Sun, but other than that they're not constrained, and no two bodies have perfectly coinciding orbital planes. However, because of the way that the solar system first formed from a spinning disk of material, most of the planets' orbital planes are quite close to each other, which is why the planets appear to travel through the same arc in our night sky, called the ecliptic. Of course, every planet with moons is a mini solar system unto itself. Most planets' big moons and rings orbit in the planet's equatorial plane. Conservation of angular momentum dictates that the orientation of a planet's equatorial plane doesn't change as the planet moves around the Sun. So sometimes a planet's equatorial plane tilts toward the Sun, and sometimes it tilts away, but twice each orbit the equatorial plane sweeps across the Sun. This is called the equinox, and it marks the changing of the seasons. At an equinox, spring arrives to a formerly shadowed pole, and autumn darkens the formerly lit pole. Earth's orbital motion can also carry it through the plane of a giant planet's rings. Because Jupiter, Saturn, Uranus, and Neptune are so much farther from the Sun than Earth is always pretty close to the Sun from those outer planets' point of view. So Earth typically crosses through the planet's equatorial planes on dates very close to an equinox. For the few tens of minutes it takes for Earth's motion to carry it across the ring plane, the rings vanish from Earth's point of view. This sounds like bad news if you like rings, but especially at Saturn, taking the rings out of the equation opens up a world of possibilities for new discoveries. With the glaring rings gone, it's possible to see otherwise invisible moons from Earth. In fact, 13 of Saturn's moons were discovered during ring plane crossings. Janus and Epimetheus were discovered during the crossing of 1966. The next crossing, in 1979 and 80, produced the discoveries of Telesto, Calypso, and Helene, just in time for Voyager mission scientists to plan for the twin spacecraft to capture photos of these tiny worlds. Ring plane crossings also aid in pinning down the orbital motions of moons. When Earth sits in the equatorial plane, Earth observers get to view the planet and moon system edge-on. The complicated dance of moons and rings, which usually plays out in 2 dimensions across the dome of the sky, gets collapsed into a single dimension as everything seems to orbit back and forth along the line of the planet's equator. As the moons dance back and forth, we see transits, where moons cross the planet. We see occultations, when the planet blocks our view of the moons. We see eclipses, as moons cast shadows onto the planet or even each other, and also when moons move into the shadow of the much bigger planet. And we see mutual events when moons cross each other. These are all fun for astronomers to watch, but they're educational too. If our knowledge of an orbit isn't perfect, our predictions of when exactly one moon crosses another could be off by a few seconds here or there. Transits of one moon across another provide exceedingly precise data for the calculation of orbits. Sometimes we're off in our predictions by more than a few seconds. During the Saturn ring plane crossing of 1995, astronomers discovered that Prometheus, one of the 2 tiny moons that shepherd Saturn's F-ring, was a full 30 minutes behind where it was predicted to be, 20 degrees off from its expected orbital position. That's the sort of puzzling observation that really gets astronomers thinking. Eventually they figured out that Prometheus is in a chaotic dance with Pandora, the other shepherd of the F-ring. The 2 moons perturb each other's orbits, slowing each other down and speeding each other up. Ring plane crossings are also excellent times for Earth-based astronomers to study Saturn's fainter rings. In fact, it was during the crossing of 1966 that astronomers discovered the E-ring. The E-ring has very little in common with the dazzlingly bright A and B rings that are visible in your backyard telescope. The E-ring is incredibly faint, but it's also vertically thick, extending thousands of kilometers above and below the ring plane. And it stretches from the edge of the rest of the ring system for hundreds of thousands of kilometers, including the orbits of the moons Mimas, Enceladus, Tethys, Dione, and Rhea. Astronomers found that the E-ring was brightest at the orbital position of Enceladus, giving the first clue that tiny Enceladus might be geologically active. We now know that Enceladus has geysers that spew tiny ice crystals into Saturn orbit and is responsible for creating the vast E-ring. Astronomers have used ring plane crossings to try to figure out just how thick the rings are. But it was surprisingly difficult to settle on that number for Saturn. Most estimates came in at about a kilometer thick. Recently, the Cassini orbiter measured the thickness of Saturn's main A and B rings and found that they're much thinner than that, only a few tens of meters thick. Why don't Earth-based astronomers get the same answer? The problem is the F-ring, the thin braided structure that orbits just outside the main A and B rings. It's ordinarily faint and difficult to spot from Earth. But near an equinox, when the sun strikes the rings from the side, the sparse, dusty particles within the F-ring scatter light in all directions, with a goodly fraction of that light bouncing back to observers on Earth. When astronomers tried to measure the thickness of Saturn's rings, they were really measuring the thickness of the F-ring. Some ring plane crossing events are better than others. Sometimes Earth crosses the ring plane just once, but sometimes there are actually 3 ring plane crossings in a row, spaced about 3 months apart. When Earth crosses the ring plane only once, Saturn is usually on the opposite side of the Sun from us and very difficult to observe. But triple crossings happen near opposition when Saturn is very high in our sky and easy to see. Ring plane crossings give us a chance to see something that's almost never visible from Earth, the dark side of the rings. Earth is usually on the sunlit side of the rings, since Earth is always within 6 degrees of the Sun as seen from Saturn. This year, when the equinox happened on August 11, the Sun went to the other side of the rings, so from Earth we were looking upon their unlit face. Today we pass to the sunlit side again, where we'll be for the next 16 years. But we can't really enjoy the view very much because this year is one of the duds, a single crossing where Saturn is lost in the Sun's glare. 1995 was a different story. Earth crossed the ring plane in May and spent the next 3 months on the shadowed side of Saturn's rings. The dense A and B rings were particularly dark, making it much easier to study the smaller moons and the faint C, D, E, and F rings. In August, Earth passed back through the plane to the sunlit side. But then Saturn's equinox happened in November, bringing darkness to the rings again for another 3 months, until Earth passed through the ring plane for the third and final time. Ring plane crossing events are rare because they depend upon the stately pace of the giant planet's orbits around the Sun, and happen only twice each orbit. Jupiter's are the most frequent because it has the shortest year, only 12 Earth years long. The most recent Jupiter ring plane crossing was just 2 months ago. Saturn ring plane crossings happen every 14 to 17 Earth years, but the next good triple crossing isn't until 2038. Uranus ring plane crossings happen only every 42 years. The last one was 2 years ago when Hubble observations showed that the ring system looked radically different from its appearance to Voyager 2 back in 1986. Finally, there's distant Neptune, which takes 165 Earth years to travel around the Sun. The last time we had a chance to observe a Neptune ring plane crossing from Earth, it was 1964, and the charge-couple device that forms the basis of most modern digital cameras hadn't yet been invented. Our next chance is still another 40 years away. It's possible to make ring plane crossings happen sooner, though. All you need is a spaceship. In 2004, the Cassini orbiter arrived at Saturn and began circling the planet, going completely around it about once or twice a month. Twice each orbit, Cassini has to pass through Saturn's ring plane. So Cassini spends roughly half its life on the unlit side of Saturn's rings, and gets numerous chances to watch Saturn's moons cross over each other in mutual events. Over the past 5 years that Cassini's been at Saturn, I've posted lots of cool animations of moons dancing past each other to my blog, and I'll have a selection of these up for you to see today.